내가 호스트를 줘야 되나? 원, 투, 원, 투. 호스트가 도움이 되지? 석훈. 아니, 태연.
저 아직 호스트 적용 안 됐습니다.
응, 응.
이제 됐습니다.
원, 투, 원, 투. 한번 말을 해볼래? 마이크 켜고.
네, 마이크 테스트 하나, 둘, 셋, 셋, 둘, 하나.
다시 한번.
마이크 테스트 하나, 둘, 셋, 셋, 둘, 하나.
오케이. 응. 네. 요거 유튜브 보이나 한번 확인해 볼래? 소리도 들리는지? 원, 투, 원, 투.
확인하고 있는데. 한번 말해 주시겠어요? 유튜브 지금
하나, 둘, 셋, 넷. 테스팅, 원, 투, 쓰리. 하나, 둘, 셋. 원, 투, 쓰리. 딜레이가 좀 있어. 원, 투, 쓰리. 딜레이가 거의 한 3, 40초 있던데. 1분. 들리긴 잘 들리나? 음. 거의 한 1분 정도 있는 것 같은데, 딜레이는. Hello, Mark.
Good to meet you.
Hi. How are you?
Very good, and you?
Yeah, it's good to meet you. Good evening, actually.
Thank you. Thank you.
It's in the morning here. What time is it there? It's like 7 before 10 a.m. here.
Oh, that's quite. It's 8 o'clock here.
Ah,
8 a.m. 8 p.m. Yes, that's right.
I think it's there's a 14-hour difference.
Well, this works well, actually. It's very nice that the difference was maybe half. We couldn't actually do this because it'd be really hard to schedule a time.
Right, yeah. Well, what's the weather like there? It's a bit cold here in Seoul. It's
Yes.
probably cold as usual there.
It actually has been a very mild winter, which means around 0 to -5 degrees. But tomorrow, we're actually getting an Arctic front,
really?
and the temperatures are going to go down to -30. So that's going to be quite cold.
Wow.
Minus Celsius. Yeah.
Maybe you can make an ice cream, you know, you can outside your house.
At those temperatures, actually, you can make snow just by boiling water and then throwing it at, you can see, I don't know if you've seen this before, but it's pretty impressive. So
Okay, great. So the last week there was a deadline for ICML. So I guess you took care of all your submitted papers.
I did, as always.
Yeah.
It's a lot of work. And how about you?
Yeah, we submitted 4 or 5 submissions. Yeah, it was a grind, but yeah, yeah. That deadlines are always hard. How many did you? Yeah, how many did you submit this time?
5.
5?
Yeah.
Oh, okay. Yeah. Good. Yeah, I guess good luck.
Same to you.
I just replied to your email regarding the YouTube. Yeah, you can check out the quality, and if we get your blessing, we'll make it available public.
Sounds good. The lighting
Okay.
looks good, so it should be fine.
Yeah, this looks good. Yeah, this is good enough. And I guess most of the time you're gonna show your presentation file.
That's true.
Instead of your face, so it should be okay. Okay, and so we have maybe 3 or 4 minutes here, and so regarding the format today, which kind of interaction, what kind of interaction do you prefer? Like, you prefer interactive session, or do you want to take Q&A right after your talk?
I'm happy to take questions during the talk, and if nobody has any questions, actually, one thing is I probably won't be able to see the chat, but if there's any questions in the chat, I'm happy for you to pause, and then we can read those questions and come back to it.
I see.
The talk has 3 parts, so I can also take a break at the end of each part and see the chat.
I see. I didn't know whether I mentioned this, but there's a small honorarium. So maybe right after this, I'll ask for your account number
For sure.
for wire transfer. Do you have like the routing number and account number, just like the US system, or?
Yes, we do.
Okay, just 1 second. Let me. Okay. Can you hear me?
Yes.
Okay, great. And so what else? the audience here, I mean, Korean students here usually tends to be shy, so they may ask probably more questions on the chat board rather than like voice. So you may maybe open up your chat, window. Okay, so maybe we can start maybe right away. Would that be okay? Can you maybe share your screen so that let me allow.
Yes, you'll allow me to share the screen.
Yeah, could you try it before we start?
Perfect. Let's see. Google Chrome. Advanced. Let me try again. Okay.
Great.
What can you see right now?
Yeah, we are seeing your title and your Google Doc page. Yes. Great. Yeah.
Perfect.
I'm in the full screen now. Yeah, looks good.
All right.
Okay, so I will start maybe introduce your background and then we'll begin.
Excellent.
Okay. So let's start. Okay, welcome to our fourth talk this semester. This is Dr. Mark G. Bellema, and he's going to talk about a very important reinforcement learning topic called distributional reinforcement learning. Let me briefly introduce him. He leads his reinforcement learning group at Google Research in Montreal, Canada. And he's an adjunct professor at McGill and University de Montreal. And he's also a core industry member for the well-known MILA, and also holds a Canada Sidecar AI chair. His group studies how artificial agents can be designed to operate in complex, time-evolving environments. Mark received his PhD from University Alberta, and he developed the highly successful arcade learning environment benchmark. By the way, was your advisor Professor Sutton then, Mark?
Actually, I work with Professor Sutton, but eventually my advisor was Professor Michael Bowling, who's worked both on the ALE and on the poker.
Okay, oh, that's good to know. And he also worked at DeepMind in London, UK. He made pioneering developments in deep reinforcement learning, proposing distributional perspective as a richer model of agent-environment interaction. So without further ado, let us welcome Dr. Mark Bellema.
All right. Thank you so much, Dr. Lee, for inviting me. This is a real honor to be able to talk to you about work we've been doing in the last few years. If there's any questions during the talk, please don't hesitate to either bring them up live or in the chat box. There's also going to be 3 parts of this talk, so I'll stop at the end of each part and we can take a look at the chat box at that point in time. Okay, so let's get started. And so the work I want to talk to you about today is distributional reinforcement learning. And essentially, this is work that I've done over the last 6 years with my colleagues, Mark Rowland and Will Dabney, and of course, many other colleagues who contributed to this effort that are listed here. And we actually just finished writing a book that should be published in May 2023. So that's this year. We're very excited about this. You can find the draft online if you'd like at the URL in the top right corner. Okay. So this talk is in a sense a little bit of a snapshot of the book, but it's also what I hope to do is, if you don't know distributional reinforcement learning, then I can introduce you to the core ideas. And if you do know it, it's a bit of I want to update your posterior on where we're at, how we think about things, and how distributional reinforcement learning can play a role in understanding artificial intelligence. So for me, probably one of the main motivations behind my research is to try to understand if we have agents operating in fairly complex environments, like the ones you're seeing here on the screen, what kind of predictions should they make about those environments? All right. So on the left-hand side, you're looking at two eyeball robots that were used in a project to study intrinsic motivation and curiosity, artificial curiosity, trying to understand how would these robots move about the world if they were to discover the world. On the right-hand side is actually a robot that was developed at the University of Alberta while I was a PhD student there, and I worked on that robot. It was called the Critterbot. And the point of the Critterbot was exactly to study how an agent equipped with a number of different sensors could effectively come to comprehend its environment by trial and error. Right? So how do we take reinforcement learning and bring it to the discovery of its environment? Okay, and so now what's interesting about this worldview is that what I've come to realize since is the importance of randomness in how we model systems. And what I mean by this is, if we look around us, most interesting problems that we encounter as intelligent agents have a part of randomness. Whether it's the randomness because the physical world is too hard to predict, right? If you're playing billiards, for example, or because there's other agents that are making decisions that you aren't aware of and only get to observe partially, right? This would be, for example, if you're trying to drive home in rush hour traffic. And it could also be due to a number of latent causes. If we're looking at health, for example, any application of reinforcement learning to health has to contend with missing variables, latent variables. And essentially, randomness and stochasticity allows us to model all of these under one unifying framework, right? So it doesn't really matter where the randomness is coming from, but it's present or it's useful to model it as such. And what's interesting is that if you look at how animals behave, you can actually find evidence that animals model this randomness in their environment. Okay, so there's a very famous experiment from the 1980s where they took the authors took birds like the one on the screen here, yellow-eyed junco, and they exposed the birds to a lottery. In fact, the birds had a choice between going left and receiving a fixed payoffs of a few seeds that they could then eat, or going right and receiving a random number of seeds, either 0 or a larger number. Okay, and the experimenters were actually able to set it up in such a way that these two levels of seed were in some sense equivalent. Okay. Now, having done this, what they found is that when the birds were well fed, they would go for the fixed amount of seeds. They preferred the safe option. But when the birds were hungry, they would prefer the lottery. Okay. And so the key here is really this reversal in preference derived from a change in state. And the fact that these birds were able to make these distinctions means that at some level, they were modeling the randomness in their environment, right? They understood that there was risk and randomness associated with the lottery. Okay. So now, what's interesting about this is that if we look at reinforcement learning, as it's mostly been applied, right, from the game of Go to Atari game playing to other video games, we typically only model the expected value, right? So I'm going to make some choices, and what I'm trying to learn is the average payoff of these choices. And this dates back all the way to Bellman, right? Who effectively said, why don't we start there? Why don't we model the expected value? That's a great place to start. The math is easy. And in most cases, it's sufficient. Now, in my experience working with the randomness in real and simulated systems, often it's not enough to just model this expected value. And the reason for this is because when we actually peek under the hood and look at the distribution of returns that could be obtained by an agent, these have fairly complex shapes. So the distributions are pretty complex. Okay, so on the top left, for example, we have work. This shows work that we did with Loon, a stratospheric balloon company, in 2020 and 2019. And so we were using reinforcement learning to fly these balloons in the stratosphere. And what we found is that because there's so much complexity and stochasticity in how these balloons are flown around according to the different winds, the outcomes, the returns that we receive are incredibly stochastic and have these very interesting distributions, right? So either heavy tail on one side or heavy tail on the other side, very rarely symmetric, very rarely Gaussian. And that's true across most of the problems where I've looked, as I said, where we've looked at the distributions. Okay, so the point of this talk really is to try to tell you a little bit how in the last 5 to 6 years, we've come to develop a mathematical language to be able to understand how to model the randomness in the outcomes that follow from decisions. Basically extend the reinforcement learning framework to deal with this randomness as a first-class citizen, okay? And so I'll give you the mathematics of it first, and then I'll talk about the computational aspects of dealing with distributions. And then I want to come back and tell you about some of the very exciting applications of distributional reinforcement learning. Okay, so let's get started. I'm sure many of you are familiar with this picture. This is a classic Markov decision process in which we have an agent that at every time step t chooses an action at. Okay, and then in response to this action, the environment will then emit a reward and emit and change the state of the system. So we denote that state by xt. And so the agent actually knows the state that it's in. It receives that reward, and then it keeps on going. And the goal of the agent is going to be to maximize how much reward, total reward it receives. Okay. In the context of distributional reinforcement learning, it's useful to actually write all of this as random variables. So this is on the top right here, are the capital letters denote random variables. X0 is the initial state, capital AT is the random action, capital RT is the random reward. Now what we do is we take all of these random variables and we actually sum up the random rewards. And we discount them appropriately, and that gives us the random return. So the random return is a sum of discounted rewards received from now until the end of time. And we write this G pi of x. Okay, it's a random variable because in general, life will be full of randomness, and that's going to cause different random outcomes, random trajectories that eventually lead to random rewards. All right, so a really useful way to understand these equations is to look at what happens in a specific trajectory. So let's start by fixing a time t, capital T, and then unrolling the trajectory from the initial state to the end of that trajectory. Okay, so I've just taken that cycle and broken it down. And to give you a sense for the kind of variable that the random return is, let me introduce this classic domain called the Cliff-World domain. So in the Cliff-World domain, the agent starts in state S and wants to reach the goal G. Okay, and just for concreteness, let's define two policies that really only differ in how they try to get to that goal G. So the safe policy is always going to try to first walk to the very end, the very back of the world, the Cliff-World, and then go towards the goal. Whereas the quick policy is just going to go right as fast as possible. Okay? And I should specify that when the agent reaches the goal, it receives a reward of +1. But if the agent happens to fall down the cliff, it receives a reward of -1. And the reason why this matters is because we're going to inject randomness in this environment, where with some small probability, the agent actually chooses, moves in a direction that was not intended at random. Okay, so with this in mind, now let's look at the possible returns that we can obtain. These are discounted sum of rewards. Because it's exactly one reward here, actually, we're only going to get values between -1 and 1. Okay, and these are going to be discounted. So the longer you take to get to the goal, the less reward you receive, the less return you receive. Now, if we look at the distributions of these two policies, there's a pretty noticeable difference. The quick policy has two sharply peaked modes, one around 1 if it reaches the goal, and one around -1 if it doesn't reach the goal. Whereas the safe policy has a small mode at -1, which would happen if it were to fall down the cliff, and a much larger distribution at positive values. And you'll notice, of course, that the values are lower, which reflects the fact that being safe has a cost. So the discounted reward is going to be smaller. Okay. And so you can see that even a very simple environment like this, if we were to try to boil this down to what is the expected return from one of these policies, we're losing out on the richness that underlies this world. Okay, so now how do we actually reason about this other than just by simulating trajectories? Well, the classic way we do this with classical reinforcement learning is we define the value function, which is the expected return. And then we have the Bellman equation, which tells us that the expected return at a given time step, at a given state, can be broken down to the expected reward plus the discounted next state expected value. And so that means we have a recursive relationship between the values at a given state and the values at the next state. Okay. And this is, in some sense, the foundation of almost all reinforcement learning algorithms. So what's great is that we can define the same kind of recursive equation between distributions. Okay, so if we start with the random return at the top, we can then define what we call the distributional Bellman equation, which essentially says that the random return at a given state, right, if it was to start my trajectory from that state and then roll it forward, is really equal in distribution to the random reward plus the random next state return. So I don't have to roll out until the end of my trajectory. Okay. And the equal in distribution here, what it means is that I really have to think of these two sets of random variables on either side of the equal sign as independent or unrelated. Okay, so I'm not trying to assign a dependence relationship between these two objects. Okay, so their distributions are the same. And essentially, what this equation says is that it's going to give us a way to find or determine the distribution of the random return by means of a bunch of operations. Okay. So the first operation is just getting the random return in the next time step. That's the blue distribution on the right-hand side. But now critically, if you discount a return, you discount a distribution, what you're going to be doing is shrinking the entire distribution towards the 0 axis. Okay, so all the returns are worth less. Then now when we add the reward, we're shifting this distribution around, we're translating it. Now, this is true if it's a deterministic reward. If the reward is random, then we actually have to convolve two random variables together and convolve the distributions. Okay, so this is the operations view. Now, if we look at the actual relationship between these distributions, we have this very nice picture that says that if I was to start with a purple distribution, well, the distributional Bellman equation says that I can break it down into, it decomposes into two distributions, which are the red distribution and the blue distribution of the next state, appropriately scaled by the reward, shifted by the reward and scaled by the discount factor, which themselves, these distributions are again a combination of future distributions. Okay, so hopefully that makes sense so far. So again, classical reinforcement learning, how would we why do we care about the value function Bellman equation? Because it gives us a way to estimate, if you will, or compute this expected return. Okay, and classically, this is embedded in what we call the Bellman operator. So the Bellman operator takes an arbitrary value function and is going to apply the operation of scaling and adding the expected reward to that collection of values. Okay, so the value function is for each state, I know its expected return. The Bellman operator takes that collection and transforms it. And dynamic programming really is the very simple algorithm that starts with an arbitrary collection of values, an arbitrary value function, and then repeatedly we apply these transformations. Okay. And what we know, we have this fundamental contractive result that tells us that as we apply the Bellman operator repeatedly, we're actually converging towards a true value function, right? A true expected return of at that stage. Okay. And so fundamentally what we say is that the Bellman operator is a contraction in supremum norm. I'm sure many of you will be familiar with this. And what we have is at every step, we're contracting by a factor of gamma. All right, so the great news is that when we look at distributions of returns, we can also define a random variable operator, which again takes an arbitrary collection of distributions, one per state, and it's going to transform these distributions in such a way that the next resulting distribution is closer to what we're looking for. Okay. And without effectively, we take these operations, and I appreciate this is still quite abstract, and I'll show you how to implement these in a second. So we take these abstract operations of scaling the distribution and transforming by the random reward, and we iteratively apply this, and the loop we call distributional dynamic program. Okay, so that loop, we start with an arbitrary set of distributions, and we keep applying these operations until we're satisfied. And the good news is we have a similar contraction result. So we have in expected returns, we have a contraction in supremum norm. In distributions, we'll have a contraction in supremum Wasserstein. Okay, and if you're curious, this is in the book, you can go take a look at the details. The good news is it means if we have a way of translating these abstract operations into computer code, well, given a specification for an MVP, we can extract those distributions. Okay, and the reason why this is valuable is because it's going to be much faster to estimate the distribution than, for example, what I had to do to get it here, which is here. What I did is I performed a Monte Carlo approximation where I ran 10,000 trajectories, collected the outcomes, and then plotted them as a histogram for you. Okay, so we wanted a solution that's better than just sampling the random variable over and over. All right. So,
can I ask a quick question?
Of course.
Yeah. Does the distributional Bellman equation, does it converge only with like Wasserstein distance? Can it be converged with any other like metric?
So not any other metric. That's a great question. We actually go in the book, we have a master theorem that states conditions under which a given metric will, the operator will be convergent under that, contractive under that metric. And so the Wasserstein metrics are actually, in some sense, the best case scenario. There are other metrics called the Kramer distances that are also not too bad. But then if you look at, say, the Kolpak-Leibler divergence or the total variation distance, we don't actually get contraction results in these distances. And this actually has implications when we want to implement these algorithms approximately. So wrong distance will result in the wrong, just not converging at all.
And it works regardless of the P value for Wasserstein P distance.
Correct.
Okay.
Exactly.
Okay. Thank you.
Thank you. This is a good question. I'll show that slide, and we can also take some questions from the chat in a second. So I just want to show you a picture, a little bit of how this dynamic programming process operates. So this is a cliff world again, and I've highlighted in color some of the states. Okay, and so every frame of this image is an additional application of the Bellman operator. And so initially, all the distributions are the same, and then with every application, we're propagating the distributions backwards and refining our approximation until at the end we have something that looks like the Monte Carlo one. Okay. And so this sort of shows you that this procedure is sound. Now, there's one thing I haven't told you about just yet, which I'm about to tell you, that I need to generate this graph, which you'll notice that there's a finite number of bins that I'm using to describe these distributions. Okay. So I'll tell you about how do we actually compute things in just a second. But before I do, maybe I can go to the chat quickly. I don't know, there are no questions right now, but if anybody wants to add questions, it's a great time to do it. Okay, well, if there are more questions later, I'll come back in the chat and we can go over these. Please don't hesitate. I'm happy to take any and all questions. All right, so now this was pretty mathematical, so I want to tell you a little bit about the computational aspects of distributional reinforcement learning. And in a nutshell, the problem when we work with distributions is that they're fundamentally infinite dimensional objects, right? They the support, even for something like the Clef world, is essentially the whole interval -1 to 1. So that means if we're trying to write this down as a computer program, we have to worry about memory and be efficient. And there's in fact NP hardness results that are well known that show that estimating the return distribution is in general NP. Okay. So this whole second section, I want to tell you a little bit about the work we've done to derive computationally efficient algorithm for approximating the return distribution function. Okay. And essentially, we're looking here at, is it accurate? Is it efficient? And following the question, is it contractive, right? So if we don't have a contractive map, then we won't have an algorithm that converges to the right solution. All right, so the most simple way to represent a distribution in distributional reinforcement learning is what we call the categorical representation, okay? And so all it does really is, suppose you start with this gray distribution that's quite complex. Well, what we're going to do is we're going to use a finite number of parameters, in this case 5, and we're going to store a probability at each of these 5 locations. Okay, so evenly spaced locations. It's a bit like a histogram from -2 to 6 in this context. Okay, and the height of the bar that describes how much probability we're assigning to each of these elements. Great. So this is good because we've gone from an infinite dimensional object to a 5-parameter object. Okay, I'm going to do this for every state. Now, how can we actually, given a distribution, find the right approximation? Well, it turns out there's a pretty simple heuristic that essentially says for each location on the support that you want to project onto, assign the probability mass in proportion to the distance to the nearest locations. And this is what the triangles are showing here. These actually triangular kernels. For example, the slightly orange line here would be the one with the highest probability mass because it's lining up with the greatest probability mass around it, right? Whereas this one, this blue Dirac delta will have much less because there's not a lot of mass around it. Okay, so we call this a categorical projection because it's actually formally a projection from the space of distributions onto the space of restricted distributions with those parameters. Okay, so again, just to recap, the problem in distributional reinforcement learning is we have to deal with infinite dimensional distributions, and if we were going to write a program to compute or approximate these, we really quickly run into an exponentially blowout in terms of memory. The solution is to add a projection operation that takes an arbitrary distribution and brings it back down to a finite number of parameters. The easiest way to do this, to embed this into a dynamic programming approach, is that we keep our 3 steps from earlier, right? Index into the collection distributions, scale by the scan, and shift by the reward. And then when we're all done with this, we then project those distributions back onto the support, the categorical support. Okay, and then we just interleave these 2 steps. Bellman operator projection, Bellman operator projection, and so on, and we repeat these steps. That's what we call categorical dynamic programming. And effectively, the video I showed you is an example of categorical dynamic programming with, in this case, I believe it's 50 different locations spaced evenly between -1. Okay. And so, as I said, the algorithm is very simple. We apply the Bellman operator, and then we project it back. So we distill down these distributions into a set of parameters, and we keep repeating this. And the good news is when we do this way, then we can actually bound the runtime cost of this algorithm and essentially have an algorithm that actually works. We can run it on regular GPU, okay, or even a CPU. All right. Now, the one downside of doing it this way is that at every step, because we're projecting to keep things finite, we're actually going to incur additional approximation error. Okay, and so we call this diffusion. And to give you a sort of an example of this, here's a very simple MVP. At the top, you have a chain where you start in state x1, and then you're going to go to state xn and receive a reward of 1. And then that's it. Now, suppose that you were to use 11 evenly spaced atom between 0 and 1. The figure is wrong; it should be 1 and not 0.5. And we try to approximate the distribution into each of these states. Well, okay, the distribution in the final state is just the Dirac at 1, and the distribution at the penultimate state will be a Dirac at gamma. Okay, and in this discount factor sort of lands in between 2 buckets. Then we have to distribute the probability mass. Okay, so the heat map on the left basically shows you how much probability mass is assigned to different return values on the y-axis. Okay, and as we go back in time from state to last state to the first state, then we see that each of these distributions can be reasonably well approximated. And I should specify these distributions are deterministic to start with. So we're only just seeing approximation error here show up as probability on different returns. When instead you start doing categorical dynamic programming, which is we interleave the Bellman operator with a projection step, at every step we're adding approximation error that compounds. So that even though the early distributions look the same, the late distributions are going to be much more spread out. Okay? So they basically diffuse their support. And so the distribution at state x1 actually has support in 5 different atoms, even though the optimal approximation would only have support of 2 atoms. Okay, and so this is what we call diffusion. This is a problem. This is an additional source of approximation error we have to contend with, which is due to the fact that otherwise we'd have we need exponential memory in general. Okay, the good news still is that we can give theoretical guarantees on the quality of the approximation and the convergence rate. And both of these are actually in a distance called the Kramer distance, which is different from the Wasserstein distance. Without going too much into detail, we can say with sufficiently many iterations, we get the right solution to converge. And that solution has an approximation error that's going to be bounded in function of course, inversely proportional to the number of locations we're using. Okay. And there's also a dependency in the discount factor. And that makes sense because the discount factor, essentially, the larger it is, the closer to 1 it is, the longer our horizon, the further into the future we're looking at. And so it's easier to make bigger approximations. In this context, on the right-hand side, Vmin and Vmax are the largest and smallest possible return. And so it also makes sense that we should have these quantities show up in the approximation error. Okay, so this is just to give you a sense for if we wanted to compute these distributions, we can derive an algorithm for which we have theoretical guarantees will give us the right answers. And that's pretty exciting. Now, in practice, sometimes we want to use the categorical representations and sometimes we want to do other things. And so I just want to leave you here with the idea that there's way more ways you can describe distributions. And if you like a different way, please use that way. Okay, so The other main container we've used is what we call the quantile representation, where I like to call it a transposed of the categorical representation. Instead of having an evenly spaced number of locations, and we move the probabilities here, we're going to keep the probabilities fixed to be uniform, but move the support around as our parameterization. And this actually was going to give us a contraction in a Wasserstein distance, which is nice. However, deriving a proper algorithm takes a bit more work. If you're curious, you can look at the book. There's also this idea of expertiles, which is taken from economics, where, again, this is a different way to represent distributions. And it turns out when we do it this way, things are more stable, but also a lot messier to deal with computation. So I think this algorithm is not quite completely understood even today. All right. So this is a bit of a whirlwind tour of how do we compute distributions and distributional reinforcement. And I'm bringing back this slide because really all of the distributions on this slide were obtained by computing, right, or learning from samples. These are real examples of how we would go about using computational tools from distributional reinforcement learning to approximate these distributions. Okay, and so on the right-hand side, you have a robotic problem from my colleagues at DeepMind. Here they were using a mixture of Gaussian. On the bottom right, you see this categorical representation being used. The top left is quantile representation with a KD smoothing to show the actual distribution. So that's the computational part of distributional reinforcement learning. And again, if you're curious for more details, please take a look at the book or ask questions. So this is another great time to ask questions before I move on to the applications of distributional reinforcement. All right. So for the rest of the talk, I want to shift gears a little bit and tell you about why learning these distributions matters in practice. Okay. And so let's go back to these birds I told you about. In reinforcement learning, and actually in operations research as well, there's this idea of risk-sensitive control. Okay. So whereas classically in reinforcement learning, we consider maximizing the expected return, right? If you're playing poker, you want to maximize your average earnings over the long term. Well, once we have the distribution handy, once we know the returns, the random nature of the returns, we can actually start maximizing other functions of the distribution. Okay, and so these are called risk measures. So we start to map the distribution of random returns to a real value. For example, we could be averse to high variance outcomes. Okay, and this is in some sense what these birds are doing when they make the choice to either go for the highest fixed number or the lottery with the highest top value. And so clearly this idea of risk-sensitive control is something that we have evidence animals. Now, what's interesting is that there's this very rich literature on doing this from a mathematical or theoretical perspective, okay? And this predates our work on distributional reinforcement learning. The way to think about how this fits in is to say, well, you can compute the distribution and then go ahead and be risk sensitive. Okay. I won't go over all of these risk criteria here, but for example, with the mean variance criteria would be, I want to maximize my mean, but I pay a penalty if I have too much variance. Or the value at risk would actually be just a quantile of a distribution. I want to maximize the 10th quantile of that distribution, and so on. Okay, so this idea of risk-sensitive control actually shows up in a number of places in the literature. One of my favorite examples is from my colleagues at Google Robotics and Google Brain, where they were looking at a robot grasping objects from a bin, as you're seeing here in the video. Okay, and this is grasping vision. And they're trying to do this as fast as possible. So there's a first step penalty and a discount factor. And the physical world, you may say, well, it's mostly deterministic, at least if we don't go into the quantum level. But in practice, once we think about a robot and it has actuation noise and the environment dynamics are not fully understood and the sensors are limited and there's function approximation and for all kinds of reasons, the world actually looks random from the robot's perspective. Okay. And so what the authors of that paper found is that if they learn to predict the distribution of outcomes, actually I can show it to you, it's in the video here. So the left-hand side, at the bottom left, sorry, is the distribution predicted by the robot in real time. Okay. And you can see it's actually quite random. It's quite a spread distribution, depending on the situation. So what they found is that if they were to just strictly start to predict the return distribution, they would achieve a higher success rate. But of course, if they actually use the distribution, they could do even better. So instead of maximizing the expected value, they would maximize a risk-sensitive version of that, of the distribution. And so actually, they did this very neat thing of they tried out both what's called risk-averse measures and risk-seeking measures. As the name implies, the risk-averse ones are going to be afraid of low value outcomes, low return outcomes, and risk-seeking ones will seek out high return. And what they found is actually that being risk-seeking was in general worse from a grasping perspective. And being just a little bit risk-averse was actually better, right? So being careful about the world, unsurprisingly, even for this robot, actually resulted in greater success rates. And to me, this is fundamental. It's essentially saying if we have a system with randomness that we don't control, but is essentially produced by this complicated environment, it might pay off to be careful about this randomness because it might reflect that there's things we don't understand. And actually, my favorite picture from the whole work is this figure that measured the number of broken fingers, a broken grip of fingers are specified during the evaluation. And what they found here is, in fact, the risk-seeking metrics resulted in more broken grip of fingers, whereas the risk-averse ones didn't break the fingers as much. So to me, this is very exciting, right? This is saying this is a simple way to turn your robot into a more gentle robot, if you will, just by learning the distribution and acting in a risk-averse manner with respect to it. Okay. So there's very recent work that apply these ideas in the context of looking for new matrix multiplication algorithms. This is work at DeepMind called Alpha Tensor. And they actually use a risk-seeking policy to incentivize the learner to go look for new solutions. So very interesting that they decided to do that. Okay. Now, it turns out actually that distributional reinforcement learning, as we've done it, has its roots in deep RL, where we combine reinforcement learning with a deep network. Okay, so the classic example, of course, is playing Atari video. And it's in a classic deep RL network. This is a DQN network you see here. We map a stack of input images to a stack of actions, or rather a stack of action values, predicting the total expected discounted reward, the return that we're going to receive if we were to choose a given action. Okay. The good news is if we want to be distributional in this setting, there's not a lot we need to do. We just need to replace the last layer of the network by one set of distribution parameters for each action. Okay, so instead of outputting a vector of size A, we output a vector of size A times M. And that's the only thing that changes. This works if we're predicting categorical distributions or quantile distributions. Okay, so we did this. And over the course of multiple experiments, repeatedly what we found is that just the very act of predicting these distributions, even if we still try to maximize expected value, results in greater performance. Okay, and so in the top right, you have the aggregate score. We call this human normalized score on over 55 Atari games for different distributional algorithm. DQN, actually, the gray bar is at the bottom, but then C51 is a categorical algorithm. QRDQN is a quantile algorithm. And we see that performance going up. This, My colleague Will Dabney worked on an older algorithm called IQN, which improved this even further. One of my students, Risham Agarwal and Aviral Kumar, had a paper that found this in a very different setting where they had massive neural networks in an offline regime, and then they found C51 made a big difference. So that's pretty exciting to me. And it's surprising because we're not actually using the distribution other than to train a network, right? But it turns out that this finding that predicting distributions improves performance is pretty widespread. So I've shown already the QT optics results. I won't go through all of these, but for example, most recently, the folks at Sony AI used DeepRL to learn to play, Gran Turismo, the racing game, and they found that making distributional predictions gave them a small edge. So very, very exciting that this just shows up everywhere. Okay. We found this again when we did multiplayer games, right? So Hanabi is a card game. There's multiplayer and cooperative, partially observable. When we tried to use a non-distributional version, nothing worked. We switched to the distributional version and it just worked beautifully. And we think here what's happening is that once you combine multi-agent, partially observable, there's so many sources of randomness and it's all sort of shifting around. It's very difficult for the non-distributional learner to make sense of what's going on, whereas a distributional learner can predict that distribution and at least do something more meaningful with it. Okay, so long story short, a large part of the research we've done since these results has been to try to understand why that's the case. And I won't have time to tell you much about this today, but I'm very excited about this line of work that essentially demonstrates that making distributions, predicting distributions results in richer state representations, right? So the networks are actually learning to predict the world more accurately, and this has all kinds of good benefits on the reinforcement learning process. Okay, so just to recap, so distributional reinforcement learning can be used to be risk sensitive. It has representational benefits in DeepRL. It also has found usefulness in computational neuroscience. Okay, so I'm very excited about this. So let me tell you a little bit about this. What you're seeing here on the screen are classic experiments from the 90s from Schultz et al. That essentially demonstrated that the dopamine neurons in the brain of monkeys behaved like a TD learning algorithm. So by this, what I mean is that these monkeys had a task to do where they would see a stimulus and then they would press a key, and if they got it right, they got a reward of juice. And on the right-hand side, you're seeing raster plots of dopamine neurons. And the top line shows the total firing of these neurons over the course of the trial. And the R bar says, here's when the reward happens. Okay, so we have three phases here. At first, the monkey just learns that the reward is a positive thing. Okay, then they learn to predict that the light predicts the reward. And actually what you see is there's a spike where the light happens and no spike at the reward because they have learned that the light will predict the reward. So it's no longer surprising. There's no longer a TD error. Okay, and the real clincher was when they showed that when you remove the reward, you actually see a negative error, but negative error at the reward, but a positive error at the light, which suggests a TD-like model for these dopamine neurons. Okay. Well, it turns out that if you go deeper into the data and look at individual neurons, you find that they all fire very differently when you subject them to random rewards. Okay, so this is an experiment where they looked at mouse neurons, mouse dopaminergic neurons, and gave them a variable amount of reward ranging from blue to red. Red is the largest, blue is the smallest. And on the left-hand side, you have what you would expect from the TD model, which is all these neurons roughly respond the same to this variability. The x-axis is how much are the neurons responding in a normalized fashion. In reality, when you look at the data, okay, it's pretty messy, but what you find is that some neurons always respond positively, no matter what the magnitude of the reward is. Some neurons always respond negatively. Okay. And this is very, very surprising, right? So these neurons are all doing different things. And well, it turns out that you can explain the behavior of these neurons in terms of distributional reinforcement learning. Okay, and without going too much into detail, because it's pretty technical, the idea is to find out where these neurons have basically a neutral point where they don't fire, and estimate how much they would fire on both sides of this reversal point. And what Dabney et al. Found is that if you measure this way, it very much looks like these neurons are encoding some kind of distributional algorithm where different neurons respond differently to randomness. And this is sort of based on the quantile line of work that Will Dabney McMorrow has done. So this is pretty exciting, and it makes sense to me because we know from these birds that we've studied in the laboratory that animals are able to represent randomness in their brains. And so it should make sense we should find correlates of this randomness in the reinforcement learning system in the brains of these animals. So there's been a bunch of papers that have since come out that are trying to explain various cognitive pathologies in terms of byproducts of risk-sensitive behavior. So I'm finding this incredibly exciting to see distributional reinforcement learning really started as a DeepRL tool start to explain the brain, essentially, right? All right, so just to conclude, one last thing that's completely different that my co-author Mark Rowland has done is to analyze the runtime of algorithms using distributional tools. And long story short, it turns out it's been known for a while that you can analyze quicksort and algorithms like quicksort that are randomized as what's called recursive distribution equations. Okay, and these equations have a similarity to distributional equations. So it turns out that we can actually use the tools of distributional RL to get a finer grained analysis of these objects. Pretty neat stuff. Mark is still working on it, so when he's done, hopefully we can have some great analysis. All right, so I've come to the end of my talk, and hopefully we'll have some time for questions. Now, at this point, I hope I've convinced you a little bit that when we look at the richness of this world, it is full of randomness. And there's all kinds of good reasons why we should want to model this randomness. And fundamentally, if we think that reinforcement learning is a good set of tools for making decisions, and then we have to make these decisions on the basis of modeling the world, then we want to be basically shifting gears and just using distributional RL to model the environments. It's, it's almost, we get it for free. And then we can start exploring much richer behaviors. So on this note, thank you so much for listening. And we have time for some questions, so I'll be happy to take some. Thank you so much.
Okay, thank you. Oh, it was great talk. Any questions from the audience, or maybe you can ask questions on the chat board? Maybe before we take a question, let me ask you a quick question about that brain experiment of monkeys. Do you think that randomness monkey brain comes from some sort of connection of neurons in the brain, or was it related to something like the kind of dynamic behavior of some sort of neurochemical, such as dopamine and things like that?
So
I mean,
I'm not
biological questions.
No, that's right. So I am unfortunately not the right person to ask these questions to. I know that there are many competing theories of what these dopamine neurons are actually doing. I saw the analysis that my colleagues did with the reversal points. It was pretty telling to me. I think one thing, I don't know if it's, I would have to ask about the data, but I believe that these recordings were done sufficiently many times and over a period of time that you're right that it's, of course there's noise in the process, but that I think what they found is repeatedly, if they give the same amount of reward, they do see a consistent behavior. Right? So one neuron will always respond to the same level of reward the same way. So it's less dependent on sort of local dynamics or temporary local dynamics, if that makes sense.
Mhm. Okay. Okay, so any questions from the audience? We have some time for taking questions.
I have one question about
Please.
risk sensitive control.
Yes.
You mentioned that alpha tensor use risk-seeking value instead of me.
Yes.
But I think that agent will eventually learn the risk seeking policy. So not a risk neutral. So I think we can use the risk sensitivity into exploration method.
Mhm.
Does it make sense?
It does. It does. So let me see if I understand correctly. So the question is whether alpha tensor use risk-seeking behavior to incentivize exploration in the algorithm. Is that right? And then, should we be doing this more broadly? Yeah. So exactly. I think it makes sense to be risk-seeking if you want to explore. I mean, we see this in children, right? We see this in teenagers where they'll take more risk maybe to explore the environment faster than they would if they were being more risk averse. In the context of something like alpha tensor, what's very interesting about exploration is that if you think about it, the space of all possible algorithms is almost infinite, right? In the context of this work, I think it's not infinite, but it's close to infinite. So exploration means something very different if you know that you'll never be able to explore all the branches. But when we think about, say, Atari game playing or Minecraft, yes, there's a lot of, there's many states, but really at some point we feel like we've explored the whole game, right? Whereas with this, really, there's always going to be algorithms you haven't explored. And so choosing the right ones to explore is incredibly important. And so being risk-seeking is one way to achieve this. Yes.
I have one more question. Then I think if we choose a risk averse policy, then fixing into the risk averse perspective might be available to explore, like, with same sense we used in risk-seeking policy. So I'm really confused about why only risk-seeking policy is available to explore.
I think we don't have definitive answers. Let me think about this. Let me try to give you a better answer. So all of this in some sense is evidence, right? We haven't made the clear connection between what is the degree to which you explore compared to how much you're risk sensitive one way or the other. But one reason why this might make sense is because as your agent is learning in the world, it's going to learn a distribution of your outcomes. And it's possible that the positive outcomes are because you did something better than expected, but you haven't been able to disentangle yet that this was actually under your control, right? So in some sense, the distributional algorithm will learn about these distributions, but whether they're under your control or not under your control. So if you're risk averse, you're staying away from these positive outcomes that you could try to get to again. Whereas if you're risk seeking, you're trying to get to these. So I appreciate this is not completely clear, but you're right that it's not a symmetric relationship. I think risk seeking for exploration works because it goes after these possible outcomes. Risk averse is not exploring because it avoids these. But it's not like it's because it's looking, maybe you're right, it would look for the worst possible outcomes, and that's a different kind of exploration. So you're right. I take it back now. being risk averse would cause you to find the worst in life.
Thank you.
There's one question from the chat board.
Yes.
Yes. Can you maybe read it for the audience and then start?
I will. So the question is, nice to meet you. Have you considered a sampling method from quantile itself as a value estimator rather than the mean? So sampling, no, but we actually have some work in preparation where we looked at using quantiles to estimate the mean. And we believe this actually is a better approach. So if you're curious, you can reach out to me and I can give you more details after the talk, but maybe you're onto something that we believe we can actually do better than just using the mean. And that's one reason why this works better in practice. So hopefully that answers the question.
Okay. Maybe actually I have like information theory background, and I mean in source coding in information theory there are a lot, I mean, rich kind of theory of so-called quantization and
yes,
vector quantization, things like that. Although it's like quantize the random variable directly, I was wondering when you talk about like categorical distribution approximation, I was wondering if there's some kind of relationship between like the source coding theory and your distributional approximation. Have you thought about that issue?
I have not thought about it, but it makes sense. Okay, so I think it's a great. I haven't seen it done. It seems like a great idea. I guess this is why you were asking about the Wasserstein distance. And I think the same way as in source coding, you might care about different properties of your distribution, whether you want to preserve the closeness. It's the same thing in reinforcement learning. So yes, it's very possible that there could be some methods and some source coding theory that would be directly applicable here for the same reason.
Yes. For example, in those theories, instead of directly kind of in terms of loss function, instead of directly measuring the distance between distributions, they try to measure like L2 kind of some sort of a mean square error in terms of the mean value of the two different distribution, and that's how they optimize the the different distribution. So I was wondering whether that kind of things can be maybe related in the future. Maybe it's future. Yeah. I mean, the quantile regression is kind of a one direction towards that avenue. I think so. Probably that's partially done already.
It is, but I think a lot remains to be understood about essentially how you encode your distributions really depends on two things. It depends on your eventual use case. So if you're maximizing expected value, you have a bit more freedom than if you're doing, say, distance of control. And actually, what's interesting is it also depends on this contraction factor, right? So you need to choose not only a distance, but actually a projection step that is going to produce a contracted map. Actually, I take it back, because even if you didn't, you could still want to have a great approximation that is convergent but not contracted. And that could be also very interesting.
I see. Yeah. Contraction is also important. Okay, there's probably one more question on the chat board, and maybe this will be the last one.
Sure, I can, and if we have time, I can also try to answer the other one quickly. Thank you for all the questions. This is great. So I think there will be a lot more multimodal tasks than single tasks in the real world. Then will distributional reinforcement learning be a necessity, not an option? Well, of course, I would love for this to be the case. I think hopefully the open source code is not too difficult to use, because I really think that in many cases, it's not a big computational difference, and it gives an additional more predictive power that comes out to be useful. Now, one thing I will say is that most of our results in the expected value setting, as I said, are when there's deep networks involved. So certainly if you're in a setting where you're estimating the mean and there's no approximation or no function approximation, it might be overkill to use distribution RL. But other than that, for example, as you say, if there's multiple complex distributions due to multimodality, that would be a great place to. Okay, and the last question is, in multi-agent setting, the randomness function of the other agents policy is convergence guaranteed? I have no idea. I think this is open as a research question. So hopefully, but people have probably thought about it, but I haven't seen any results in that space.
Okay, great. Okay, unless there are any other questions, I really appreciate your great talk and your time in this actually evening, and I think it was quite inspirational to me and maybe many other graduate students here. Hopefully we can meet maybe in person in the future conferences.
That would be lovely.
Yeah, and yes. I really thank you for your time today.
Thank you so much for letting me present. Have a good day. Bye-bye.
Okay, thanks a lot. Bye.